Hi everyone. Today's lesson is on dividing radicals. So I hope you reviewed your other operations with radicals. So simplifying radicals, adding and subtracting radicals, multiplying radicals. That was last week's, I believe it was Thursday's lesson. Because you are going to need to know how to at least simplify radicals in order to divide. I also want to talk about some other prior knowledge you are going to need for this lesson. So since we are dividing and we are going to have variables involved, with variables comes exponents. So just a reminder, when you are dividing variables or anything that has exponents, remember that you subtract the exponents. So for example, if you have x to the fifth over x squared, you're dividing x to the fifth by x squared. That would equal x cubed because you're subtracting 5 and 2. So 5 minus 2 is 3. Now, if the larger exponent is in the denominator, so for example, if you had, say, x over x to the fourth, so technically that's x to the first over x to the fourth. Since the larger exponent is in the denominator, so you would subtract 4 minus 1, which would give you 3, but that would stay in the denominator. So your answer would be 1 over x cubed. So I just wanted to refresh your memory on that because you are going to need that for today's lesson. Also, remember how to rewrite numbers using their prime factors. We talked about that before with birthday cake. And some of you like to use the factor trees, which is fine. So for example, say 16. 16 can be broken up into 2 times 2 times 2 times 2, or 2 to the fourth. Another example, 20. 20 can be broken down into its prime factors as 2 times 2 times 5. So just remember that you can always break down those numbers into their prime factors. Okay, so I just wanted to refresh your memory on those things. I think that will help with today's lesson. With today's lesson, I did put the notes on Google Classroom, but if you don't have a printer, please feel free to just copy down the notes on lined paper. You don't need graph paper this time. It's just really straightforward. So if you don't feel like printing it out, feel free to copy it on lined paper. Okay, guys. Okay, so dividing radicals. So far we've talked about simplifying radicals, adding and subtracting radicals, multiplying radicals, and now we are on dividing radicals. Similar to multiplying radicals, we can only divide radicals if they have the same index. So remember, index is that little number in the corner of the check mark. So for example, if we have, say, the cubed root of x over the cubed root of x squared, we could divide those. This is the same as writing it as one large radical as the cubed root of x over x squared. These are the same thing, just represented two different ways. So to divide, what steps do we take to divide? First thing you want to do is actually divide, if you can. So if you can, for example, if you had like 2 over 4, and you could simplify that to 1 over 2. If you had x over x squared, and you could simplify that to 1 over x. You want to do that. You want to simplify it, divide it, make it easier for yourself. Then you would simplify the numerator and denominator separately. So making your groupings, pulling things outside of the root if you can. And last but not least, rationalize the denominator if needed. This we will talk more about in a second. Rationalizing the denominator actually leads us to this next part. In math, there's a few things we never want in the denominator of a fraction. One thing we've talked about is how we don't want 0 in the denominator of a fraction, right? That's a big no-no. Another thing we don't want in the denominator of a fraction is I. We talked about that back when we were talking about imaginary numbers, and we couldn't have I in the denominator of a fraction. The reason why we couldn't have I in the denominator of a fraction is actually because of what I represents. I, in case you don't remember, is equal to the square root of -1. So actually, what we never want is a radical or a root in the denominator of our final answer. So that was the reason why we couldn't have I in our denominator. And right now, we also can't have radicals in the denominator of our final answer. Now, sometimes the problem will simplify and we won't have a radical left in our final answer. Sometimes we will, and that's where step 3 comes in, where we have to rationalize the denominator. So let's look at these two examples and hopefully you'll kind of see what I mean. We'll go through these steps and it'll be a little bit clearer. So looking at example 1, so we have the cubed root of 27x squared divided by 2xy. So first you want to check and see if there's anything you can divide. 27 is not divisible by 2, so we are going to leave that. X squared over x, we can simplify those when you are dividing. So remember here we have an exponent of 1 for x. When you're dividing, you subtract the exponents. So here we are left with x to the first on top. Y, we don't have anything to simplify with, so that just leaves us with y in the denominator. Now, if we split this up into two separate radicals, because these are equivalent, just like we talked about up here. So notice how we are left with a radical in the denominator. And here, this doesn't simplify. The cubed root of 2y, we cannot simplify. We don't have any groups of 3 that we can take out. We can simplify part of the numerator. So 27, if you break that down, either using the birthday cake, oopsie, that should be a 9. If you break down 27 using either the birthday cake, or if you already know the cubed root of 27 is 3. So that comes out, and then we're left with the cubed root of x underneath. But we're left with a radical in the denominator. So here, this is actually not finished. And we'll talk more about that on the next page. The reason why is because we have a radical in the denominator. What we want to get in the denominator is a whole number, a whole expression, with no more radical symbol. Let's look at our second example. Okay, so again, if you want to rewrite this, now remember these two are equivalent, but sometimes it's easier to see visually the division all together under the root, but it all depends on your personal preference. But again, these two are equivalent, so you can write it either way and you could just divide it either way. So here, this is actually divisible. So if we divide this, so 100 divided by 4, so we get 25. X to the 5th over x cubed, if you subtract those, you get x squared. And technically in your denominator, you're not left with 0. You don't get 0 in the denominator. Technically, you're left with 1. but the square root of 1 is just 1. So we actually have a whole number in our denominator, which is a good sign. And that leaves us with just our numerator. So here, the square root of 25x squared. So again, you could either do a birthday cake for 25, or you might know, and hopefully you know, what the square root of 25 is. So this would simplify, I'm just gonna write it a little bit farther down, to 5, and then x squared, the square root of x squared is just x, because technically that's two groups of x. You would have x times x. Remember, the index here is 2. Now, a few things. So the good news is this simplifies completely. We do not have a radical in the denominator. We would not have to rationalize the denominator. Second thing, this is not finished. Now, if you think back to weeks ago now, when we were simplifying, adding, multiplying, we always kept on telling you about absolute value. So we use absolute value when we have an even index. So 2 is even, we have an even index, and we get an odd exponent on a variable outside of the square root. So here, the exponent's not written, but it's 1. 1 is an odd number. So here we need absolute value around x. And this would be our final answer for this problem. So again, this problem does not require rationalizing the denominator. This is finished now. This problem, however, is not finished because we have a radical left in the denominator, which is going to require us to rationalize the denominator. Okay, so rationalizing the denominator. Rationalizing the denominator can be a bit of a complicated process, so I'm going to try and make it as simple and straightforward as possible. So in order to do that, I want to talk about kind of the concepts that go behind rationalizing the denominator and why does it work out the way it does. So first we need to think about some things that are just true in math. So first of all, the fact that multiplying a fraction by 1 does not change its value, right? Multiplying anything by 1 doesn't change its value. It's going to stay the same. Second thing, another math fact, any expression divided by itself is equal to 1. So for example, 2 divided by 2 equals 1. X squared divided by x squared equals 1. Whenever you divide something by itself, it always equals 1. So how do we use this to rationalize the denominator? So the reason we have to rationalize the denominator is to get rid of a radical in the denominator. That is a big no-no in math, right? We don't want 0 in the denominator of a fraction. We don't want I in the denominator of a fraction. We do not want a radical in the denominator of a fraction. So how do we do that? How do we get rid of a radical? It requires us to multiply the numerator and denominator by the radical that would make the denominator perfect. And this perfect means perfect squares, perfect cubes, things, groups that are going to match the index. So think back to when you were simplifying, right? When you're making your birthday cake, when you're writing out all your x's, you were looking for groups that match the index. That's what we want, because we want to be able to simplify the denominator completely so we don't have a root or a radical anymore. So you want to think, how many more groups do you need to match the index? Okay, so let's see what that means. So our first example at the bottom here, we have 2 divided by the square root of 3x cubed. So thinking back to the front, first thing you want to check and see is, can you divide anything? Now here, we can't divide anything because the numerator does not have a square root. So it actually doesn't even have the same index as the denominator. So there's no way, even if there was something in common here, there's no way we could simplify that. Now you could simplify this because x cubed you could break down. So I'm just going to rewrite that. Okay, x cubed you could break down into x times x times x. And here, so remember our index is not written, so it's automatically a 2. So we're looking for groups of 2 of the same thing. Now, I'm not going to simplify it yet because we can simplify at the end, but I'm going to show you how we're going to rationalize the denominator. So notice in the denominator, we have a group of 2 right here. We have 2 x's, but then we'd have this 3 and this other x left over. So right now our denominator is not technically perfect because we would still have 2 things left under the root if we tried to simplify it. Now that requires us to rationalize the denominator. So this means we're going to have to multiply both the numerator and the denominator by the same thing, but we're multiplying by a radical that would make the denominator perfect. Okay, so what does that mean? So that means, all right, we have these 2 groups of x here, right? That's fine. We could simplify that out if we wanted to. But we don't have 2 3s, and we don't have another x to pair this with. So that's what we're missing. And that means that's what we're going to have to multiply by. We're missing another 3. We're missing another x. So when you're multiplying by kind of what you're missing in order to get those groups of 2. So you need groups of 2 in order to simplify the denominator completely. Okay, whatever you multiply by in the denominator, you're multiplying by in the numerator as well. And that goes back to 1 and 2. Because look at this fraction here. Square root of 3x over the square root of 3x. Technically, that would be equal to, if you simplify that, that would be the same as 1, right? You're dividing something by itself. And if we multiply something by 1, we're not changing the value, but this is allowing us to get rid of the root in the denominator. Okay. So what happens now when we multiply? So remember, when we multiply straight across. This 2 is not under a square root, so it's going to stay in front of the square root of 3x. Now in the bottom here, I'm going to leave this all separate, but I'm just going to put it in order. So I'm going to put the 3 and the 3 together, and then I'm going to put all the x's together. And notice what happens. So again, our index is 2, and notice now we have groups of 2 of everything. And that's what we want, because when we have groups of 2, that's going to allow us to simplify this completely. So we have 2 groups of 3. So if we simplify that, a 3 is going to come out. A group of 2 x's, and x is going to come out. Another 2 x's, another x is going to come out. This is going back to simplifying, the first thing you guys learned with radicals. So notice once we simplify this, we no longer have a radical in the denominator, and winner, winner, chicken dinner, that's what we want. We don't want a radical in the denominator. That's what we're trying to get rid of. So that's why we had to go through all those steps and rationalize. So now I'm just going to write this a little bit nicer, because we know x times x is x squared. Do we need absolute value? No, because we have an even exponent here. Okay, and that is your final answer. Now you do always want to check and see, can you simplify anything else? Like, can you divide 2 and 3? Can you simplify that? Can you simplify anything under this square root? And here the answer is no, but that's only something you want to check for. Okay guys, I was just editing the video and I was thinking some of you are probably thinking in your head, well, Mr. Rock, why can't we divide the 3 that's under the square root and the 3 that's in the denominator? And the reason why is because the 3 that's in the denominator is not also under a square root. Remember, in order to divide them, they have to have the same index. So since they're both not under a root, you cannot divide them. Okay, so I just wanted to clarify that. Okay, so just to summarize, so going back to our first step, so notice how I just rewrote this, kind of broke it down to see what groups we had and how it matched up with the index. And then your index is your key here. Your index tells you how many groups you have and how many more you need. So here we only had 1, 3. That told me I needed another one in order to get that group of 2. In order to simplify it. We had 2 x's, but then we had this one left over. That one needed its buddy in order to simplify. So when you're rationalizing and when you're thinking about what to multiply, you need to think about what are you missing. So what are you missing in order to make the denominator perfect? So again, thinking back to how many more groups do you need to match the index? Okay, so moving on to number 2. So first you want to check and see, is there anything you could divide by? Here, again, they have the same index. So we can divide if they have something in common. So here, 15 and 20, those are both divisible by 5. We could simplify those. X cubed and x to the 5th, those are both divisible by x cubed. Y to the 7th and y cubed are both divisible by y cubed. So let's go ahead and simplify this, make it a little bit easier on ourselves. Now notice the 2 and the 5 in front. Those are just coefficients. We can't simplify those right now, so those are just gonna stay as they are. Okay, 15 divided by 5 is 3. If we divide by x cubed, that gets rid of this on top. Y to the 7th divided by y cubed just leaves us with a y to the 4th in the numerator. In the denominator, 20 divided by 5 is 4. X to the 5th divided by x cubed is x squared. So remember, you subtract exponents when you're dividing. Y cubed divided by y cubed is just 1. So you know what I'm going to do? I'm just going to shorten this a little bit. Okay. Next, you want to check and see, can you simplify? So let's first look at our denominator, because usually that's what we have to worry about, whether or not we have to rationalize. And looking at our denominator, well, I know 4 is a perfect square. X squared is a perfect square. If I take the square root of both of those, square root of 4 is 2. Square root of x squared is x. And notice, we're not going to have to rationalize. That simplifies completely. We don't have a radical in the denominator, so that's good news for us. Now, in the numerator, all right, so we have 2. Can't simplify the square root of 3, but y to the 4th, that gives us, I'll just write that out. That gives us 4 y's. So 2 groups of 2. So continuing down here, so that's going to be y times y if we bring out one of each. Square root of 3 is left underneath. On the bottom, multiplying those. Okay, and then rewriting it. Okay, is there anything else we need to do? You should have said yes. We have an even index. Our index is 2. Look here, we got an odd exponent. We need absolute value. You always need to keep that in the back of your mind, guys, whether or not you're going to need that absolute value. So you know what? Let me make a little note down here just to remind you. So absolute value is when you have an even index odd exponent outside. Okay, let's go through example or number 3 together, and then I'll let you guys try the rest on your own, see if you can get the hang of it. Okay, so number 3, let's first see if we could divide anything. So see if we have anything in common. And here I just noticed we have an x here and an x down here. So let's simplify that. So remember, when you're dividing, you're subtracting exponents. And when you're subtracting the higher one from the lower one. And wherever that higher one is where it's going to stay. So here, our higher exponent was in the denominator, so it's going to stay in the denominator. Now, there's nothing else I can simplify. And if I break this up, we're still left with a radical. And that means we're still left with a radical in the denominator, which means we're going to have to rationalize the denominator. Now, think back to the first problem we did and how I broke it down and I rewrote it. I'm going to do that again here, but I'm not just going to do it with the variable, I'm also going to do it with the number. So think back to your birthday cakes or your prime factorization, right? Breaking down 4. So 4 So right now I'm just rewriting it, I'm just recopying. 4 is going to be rewritten as 2 times 2, and then I'm just gonna rewrite those x's. Okay, so we have to rationalize. So again, you have to think about your index. 5, we need groups of 5. Now notice here, we don't have any groups of 5. So we have 2 2's, we have 3 x's, but no groups of 5. We want to get groups of 5. And you know what? I'm running out of room here, so I'm just going to recopy this down here. And just so it'll be clear for you guys. So I'm just recopying that same exact thing I just wrote down. Okay. We want a group of 5. So that means we need 5 2's. Because in order to simplify this, we need 5 2's in order to take that 2 out of the radical. If you have 2 2's and you want to get 5, how many more do you need? And the answer is 3. So I need 3 more 2's, right? Because when I multiply these together, these 2's and these 3, when I put them together, I'm going to have 5 2's. Here I have 3 x's, so I'm going to need 2 more to get a group of 5 in the end. So you need to think, how many more do you need to get that group of 5? Key thing, whatever you're multiplying by on the bottom, you're just going to copy on the top. And then the next step is just to multiply across. So this should be the hardest part, is figuring out what do you need to multiply by. But just be careful you don't make little mistakes in other places, because I've seen that before. Okay, so multiplying across. Now multiplying across, I'm just going to put those in order in the top. And in the top, see, the good thing here, since it's all broken down, you can see we don't have any groups of 5. So we're not going to be able to simplify this numerator. So I'm just going to rewrite that in a second. In the denominator, so here's what you should get. You should get your 5 groups of 2, right? If I put these 2 and these 3 together, and then you should get your 5 groups of x's. Okay, 5 because that's the index again. So 5 2's, 5 x's, I can simplify that into just 2x. Again, in the numerator, you can't simplify that as far as taking anything out, but you're just going to rewrite it. So multiplying 2 times 2 times 2 times 3, you get 24 x squared. So this is your final answer. Again, asking yourself, is there anything you're missing? Anything else you need to do? Here, the answer is no. You don't need absolute value because you do not have an even index that you are working with. Now, some people, I'm sorry guys, I just noticed I was off screen. Sorry, this is your final answer. Some people will try and go a step further and divide this, but you cannot. Please do not divide these. Remember, in order to divide, you have to have the same index. But if you only have a radical in one spot and not the other, you can't simplify those. If this was under a radical with an index of 5, you could, but it's not. So you can't simplify that. Okay, so that is your final answer. So what I'd like you to do now is to try the other 3 problems on here on this sheet as best you can. Please feel free again to ask me any questions, email me, text me on Remind, post on Google Classroom. And I hope to hear from you soon. All right, good luck guys.